Welcome. We are discussing last lecture the injection metallurgy, and we are discussing the various injection techniques. There are basically two techniques are there for injecting the reactive and volatile calcium powder into the liquid melt. One is the submerge, there is the injection of the powder using submerged lens, or you can inject it by cold wear injection. They are telling cold wear is nothing but is a hollow cylindrical casing which is packed with the calcium powder, and it looks like a ware. That's why it is called the cold ware. So, in this lecture basically we will discuss about the modeling, melting sequence and the effect of operating parameters on the melting of cold ware. So, first of all we will just give a brief introduction about the cold ware injection, its advantages and challenges. Then the melting sequence of the cold ware under different operating parameters and effect of operating parameters on melting sequence. Now, what is cold ware? First question is that what is cold ware? And as I said, cold ware is a hollow cylindrical casing made of mostly by the mild steel. It is casing made of mild steel, and it is packed with calcium powder, and it has an appearance of an ware. That is why it is called a cold ware. It is a hollow mild steel casing which is packed with calcium powder, and it is look like this. You can find this is the hollow casing, and then inside this is the powder is packed, and it looks like a ware, and this ware can be rolled around also. This is the ware, and in the roll form it is like this. Okay, so that's why it is called a cold ware, and and this cold ware, and you just inject this cold ware in the liquid melt, and when the ware melts, it releases the powder. That is the way you can release the powder in a submerged condition. Thus, the powder is released into the liquid. Okay. And it is a very less cumbersome process compared to the lens injection. Submerged lens injection is little bit cumbersome, and because here the powder material is with the help of a carrier gas is injected into the bottom into the liquid bath, and that is little cumbersome, and also this method is less cumbersome and cost effective from that point of view. And another problem is that in case of the submerged powder injection, around 40% powder move off basically through the liquid as particle inside the bubble, and during the rise this particle do not participate significantly into the mass transfer process because they are inside the bubble, and then that is the problem. And 40% of this particle, so you can see during powder injection through submerged injection lens with the carrier gas, around 40% particle moves as particle inside the bubble, and which cannot participate much into the impurity transfer during its transit through the liquid when they are moving up from the bottom to the top slag. After joining the top slag, obviously they can participate, but during their rise you cannot utilize them properly. There is some amount of reaction will be there, but less. So that is there, but here that problem is not there. And as I said, and then powder injection process, that is the cold ware injection is like this. It is rolled here, and then with the help of a feeder you can just feed like this. A wire is injected vertically inside the liquid, it melts and releases the powder inside the liquid. Challenges of cold ware injection, as I said, the calcium is volatile and very reactive. So, and it is very difficult to retain into the bath. Since it is volatile, it is very difficult to retain in the bath because it will form a bubble and go away from the system. So, it is required to be fed at the bottom of the bath for the maximum assimilation of the calcium, because if you just feed at the bottom of the bath, then during the rise of the bubble, calcium bubble, you can utilize them, or your residence time of the calcium powder will be more inside the liquid, right. Second thing is that, but it is in an opaque system like liquid steel, it is very difficult to visualize where the ware is melting and releasing the powder. So, after entering the bath, the powder can be released just after entering it, or it can be released in the midway, it can be released at the bottom, and the wire may not melt even after reaching the bottom. So, all possibilities are there. At the same time, you cannot see where the wire is melting. This is the challenge. So, you have to find out the means to see where the wire is melting. So, mathematical modeling can be helpful in this point of view. And once you know how much, using mathematical model, how much the wire is going, and then you can optimize the parameter such that the wire melts just at the bottom of the bath. Because if it melts at the bottom of the bath, then the powder will be released at the bottom of the bath, and then it can get the maximum residence time during its rise. So, that thing is there. Tailor the operating parameters to release the powder just at the bottom of the ladle to maximize the calcium recovery. Okay. So, this thing can be done by using a mathematical model. Another important parameter is that how much the wire has to be added, how much calcium I need in the bath to form the appropriate inclusion. This is another question. So, that thing also has to be identified. How much wire should I melt? Once I define, that is once I say there is the wire is melting at the bath, recovery is maximum, but how much calcium I need into the liquid bath, okay, such that it can form an appropriate conclusion. That is also another question. Now, as I said, it is the mathematical modeling that comes to our help to identify where the wire is melting, what is the location of where it is melting and releasing the powder. So, a mathematical model has been developed and it is reported in literature. And what is our objective? First objective is to understand the mechanism of wire melting. That is how the wire melting. As soon as the wire moves into the bath, what are the sequence? In fact, when the wire enters into the bath, a steel shell forms on the on the wire surface. It is supposed to be because wire will act as a coolant, because it is at room temperature. As soon as you enter it, there will be localized cooling at the surface. Okay, as a result, a steel shell will form. Then the steel shell will melt, then the casing will melt, and finally the powder will be released. The process may be even little complicated, but we need to understand that is how long this shell forms, what is the maximum thickness it goes, and then melts, and then casing melts. So, how much time does it take totally for all this operation? So, first of all, we have to understand, first thing is that mechanism of wire melting, how it, what are the mechanisms. Second is the distance travelled by the wire, before it melt into the bath, how much distance it can wear. So, if you shell forms, shell dissolves, and then powder get released, casing dissolves and powder released. So, all this process, how much time does it take, and such that we can locate the point of powder release. Okay. So, these two things, understanding the mechanism of wire melting, distance traversed by the wire before it melts in the bath, and tailoring the operating parameters finally to release the powder just at the bottom of the ladle to maximize the recovery. This is the major objective of the mathematical model. So, mathematical formulation, it is basically a one-dimensional transient moving boundary problem. Why it is one-dimensional? Because the wire is the length is length is much higher compared to its radius. So, heat basically temperature gradient exists across the radius. So, it is temperature, it is perfectly one-dimensional problem, heat transfer problem. Transient, if you move with the wire, it is a transient phenomena, because you will experience a particular location will experience a different temperature with time. It will not be steady at all. Okay. So, it is a transient phenomena. And moving boundary, why it is so? This is moving boundary problem perfectly. So, this is the cross section of the wire when you take after it has immersed a certain distance into the liquid melt through a slag layer also. So, then what you can find, it is the powder inside, and then you have the what is that? You have the casing. Just above the casing you have some slag layer, because it first entered the slag. So, a slag layer forms, and then over that you have a metal layer also, that is the metal shell. Okay. So, this is what does it look like, a composite structure as you can find. So powder, then casing, then your slag layer and the metal shell. Okay, so at certain time, so it is basically developing, that is these shells are developing, and then again the metal shell will dissolve, and then the slag shell will dissolve, casing will dissolve, and then the powder will get released. So this is all the process that will take place, sequence of process will take place, and then the powder will be released. Okay. So that's why it is a moving boundary problem, that is the boundary is increasing and then decreasing, and finally powder get released. Okay. And also you can see that we have considered a contact resistance just at the casing slag interface, because the slag is solidifying over a solid casing, and since it is slag oxide basically, and casing is mainly made of the metal, that is, or alloy, that is there is a mild steel. Okay, so we consider there will be some mismatch. Okay, that is the slag will not fully wet the casing surface, that we assume as a result you will have some contact resistance. Unlike to that, in the slag metal interface we may not find this type of disparities or asperities at the interface, because liquid steel will much more weight the much softer slag shell. Okay, so wettability will be much higher. So here we can consider definitely a contact resistance here. So this is, and we have solved simply one dimensional transient moving boundary problem. Okay. Now we see some results, that is the routes of melting. What are we have basically identified 4 routes of melting, depending on we have slag cover or not, or we have a low superheat or a high superheat. First thing is that in absence of slag cover and high superheat, the route 1 we are telling. So let's see what is there. First you have the cold wear, before injection you have this thing, and then as soon as it enters into the bath, liquid bath, a steel shell forms. As I said, because it acts as a coolant, and if I just describe it little elaborately, suppose you have this is suppose your cold wear, that is the wear, and this is the liquid steel, and you have some thermal boundary layer. This is the thermal boundary layer, and you have a temperature gradient like this also. So this is the TL, liquid temperature, and this is basically you will have some shell will be there. So here TM, I can say TM. Okay, and then this is your gradient. Okay, I will talk about it. Is better if you just see, it's not too much, because there is a gradient and then there is a further steeper gradient. So I can put it a much steeper gradient here, because it is the room temperature, interior of the wear is the room temperature, so much steeper gradient is there. Okay, so this is the temperature. Suppose this is the center of the wear, center of the wear. So what we can find is that here across the thermal boundary layer, the temperature gradient is not that much. It will, we can expect it is the melting temperature at the surface, because you have some shell formation. So at the surface you can assume it is the melting temperature or the liquidus temperature, and this is the actual the liquid temperature. This is basically the superheat, and superheat is not very high. So this is the temperature gradient will be less, but here if you see from TM to the interior, because it is a 30 degree centigrade, so temperature gradient is very steep inside. So here if you say this is a flux will go, that is F1, and this is the flux that is coming F2, and then initially obviously F1 is much greater than F2. Initially F1, the flux that is going inside the wear is much greater than the flux that is coming from the liquid to the wear liquid interface. So this flux is much greater. As a result, you have a localized cooling, and that gives basically F1 minus F2 gives you the that is the imbalance of heat. There is a localized cooling. As a result, shell forms. And how long the shell forms? As long as F1, because with time what happens? With time, this gradient will decrease with time. If you see the gradient will decrease with time. After some time it will be here, after some time it will be here. So with increase in time, the gradient will decrease. So as a result, F1 with increase in time, F1 will decrease with time, F1 will decrease with time, right? With time F1 will decrease. So as a result, your shell will grow. As long as F1 is greater than F2, shell will grow. But when F1 become equal to F2, that is the maximum shell growth. And then when F2 exceeds F1, then melting take place. So this is the shell formation, and as soon as F2 become equal to, so F1 greater than F2, okay, that is the shell formation. So F1 is equal to F2 maximum shell thickness then when F2 greater than F1, then shell starts dissolving. Okay. So then the shell starts dissolving. So this is the way. So first shell formation F1 greater than F2, then F1 is equal to F2 maximum shell, and then the shell start dissolving. And so that is what is happening. First the steel shell forms, you can find here, and the shell grows to the maximum thickness, and then the steel shell melts back. So it happens basically here, basically your F2 greater than F1, right? Here F1 is equal to F2, and there basically F1 is F1 greater than F2, F2 greater than F1. So that is basically happening in this case. Shell, and then your direct heating of the casing is taking place, then the melting of the casing also taking place here, and then the powder is released, the solid powder is getting released finally, okay. So that are telling that finally the solid powder, basically it is the high superheat there. So superheat high means your F2 is little bit higher, bigger, so it doesn't give too much of time for the ware to melt. So all this sequence take place, but it is much faster because of high superheat, and finally the powder is released in the form of a preheated powder. So it is not molten, preheated powder get released, okay. So let us see the next case what happens. In this case your slag is not there, but the low superheat, here basically the superheat is low. In that case what happened, what difference you can find, that you can find the steel shell grows to a maximum thickness. Here the thickness is greater than the condition when the superheat was high. Here the superheat is low. If the superheat is low, the shell will grow to the maximum extent, right? Because F2 is little higher here, F2 is higher, that's why. So as a result, because of low superheat, all the same sequence take place, but it process takes little more time because of higher thickness of the shell. So growing shell and dissolving it takes more time. So by that time the powder also get preheated beyond its melting temperature, and powder is molten when it is released. So release the molten powder. So this is from the model calculation is shown. The basic difference is that without slag, and when it is low superheat, that is the where takes more time for its melting, because the shell grow to a maximum extent, and shell growth and dissolution take more time, right? So that is the thing. So next we see the third case, that is now the presence of slag cover. Suppose you have a slag cover is there, and then you have a high superheat, then what is the condition? In this similar sequence is there. Now only one, because since the slag is present, now here two layer will form. You will have a slag layer first, followed by a metal layer, that is the steel layer, okay. So that is the thing, this is the first slag shell form, here is the slag shell form, and then the first steel shell forms, then the steel shell grows, steel shell melts back, and then the slag shell melts back, direct heating of the casing, melting of the casing, and then powder release. Powder again here it is released in the solid form, but it is little more preheated. Okay, so it is compared to the case without slag and with slag is there, you have a extra slag layer that is forming. As a result, you are giving more time, basically more time for melting. So where it takes little more time for melting, but because of high superheat, The increase in the time also not very high, and the powder still reduced in the preheated solid powder form. Okay. So next we get, that is you have a slag layer as well as a low superheat. Now in this case what you can find, same sequence, a slag shell forms, then that is your metal shell, steel shell form, then the steel shell dissolve, slag shell dissolve, casing dissolves, powder get released. But here some unique phenomena take place. What is that? Because it is a low superheat, because when the steel shell grows, because steel shell grows to a maximum, it is little more, thickness of the steel shell that is grow here is more, right? As a result, it takes more time for forming the steel shell over the slag shell. The steel shell is forming, and the steel shell is forming to a greater thickness, and then as a result, for steel shell to grow to a greater thickness and then melting back, it gives more time. Okay, and by that time what is happening is your slag shell inside will be preheated, obviously will be preheated, and the time of preheating may be little higher. Here it is higher. As a result, what happens, the steel shell can attain this liquidus. Okay, it will be preheated beyond this liquidus temperature. As a result, what happens, the slag shell get liquid before the steel shell completely melts back. So this is the unique thing is happening, that is your steel shell, slag shell forms, and the steel shell is forming and the steel shell is melting back. But since the steel shell formation and melting taking more time, the slag shell inside is preheated beyond this melting temperature, so slag shell melts. And if it melts, what happens? Immediately the contact between the casing and the slag become much better. Basically, the liquid slag will wet the casing surface much more, right? So as a result, what happened, the contact resistance at the steel shell, there is a casing and the slag there, that was the contact resistance were there, that resistance will vanish immediately, because the liquid slag will wet the casing surface perfectly. So if that contact resistance suddenly vanishes, what will happen? The heat flux towards the interior will increase, suddenly again it will increase. So the flux inside the core will suddenly increase. As a result, what will happen? The steel shell, again there will be localized cooling, and the steel shell will again further start growing. You can see that is called the secondary growth of the steel shell. You can see interior there is a liquid slag shell is there, and the steel shell again growing, because suddenly the heat flux inside increased, and that gives a additional cooling, and that basically give rise to an growth of the shell thickness, right? So this is called the secondary growth of the steel shell. So then after growing, then the again steel shell will dissolve, and finally the slag shell is already molten, and the casing will be exposed, and then the powder will be released. Casing will be exposed, casing will also melt, and the powder will be exposed, but here the powder is exposed in the form of a molten powder. So basically what is happening at the low superheat with a slag, we are finding a unique phenomena where a secondary growth of the steel shell take place. Okay, because of contact resistance suddenly vanishes when the inside slag layer become liquid and it wet the casing surface perfectly. Okay, so this is a unique phenomena. This basically delays the melting process. So that's why you can see here also, that is we have drawn here the radius, instantaneous radius, how it is evolution of the radius of the wear with the time. You can see in presence of slag, this is the curve in presence of slag. So in presence of slag, wear thickness is going to a bigger, okay, and then it will go to bigger, and then it is coming down, and then there is a secondary growth of the steel shell, and then coming down to a zero value. Okay, but in contrast, if you see without slag, then the growth is this much only. That is, in case of the slag, obviously it is higher because two shells are forming, one is the slag shell and the steel shell, that's why the radius is higher here. and here it is due to the secondary growth of the steel shell. And in case of without slag, your total thickness is less because only one shell is forming, and then you can see there is no secondary growth of steel shell. You can see the casing is exposed to a bigger time and then it is coming down. Because casing is exposed for a bigger time, thing is that because it has not been properly preheated, and in this case it has been finally totally preheated. So casing doesn't take, when it is coming here at this position, doesn't take too much time for melting, because it was already too much of preheated, because a lot of time has been gone where the casing has been preheated and then coming down. So this is the basically effect of the slag layer. Effect of the slag layer is mainly is that it delays the melting process. And effect of bath superheat, if you see, red is the high superheat. You can see in all the red cases the melting time is much less, because when the superheat is high, then F2 is little bit higher. Okay, so heat flux from the liquid to the interface, that is the where liquid interface is much through the thermal boundary layer, the heat flux is higher. As a result, the melting process become faster, as you can find. And all other case are the low superheat case are there. This is there, and this case 3A basically. In this case, there is no secondary growth. In case of the 2A and 1A, you have, that is the speed, depending on the speed also, that is the speed is 2 meter, 3 meter and 4 meter. So, because if you increase the speed, then also the heat transfer coefficient at the your where liquid interface at the thermal boundary layer increases also. Okay, so with increase in the speed time, because it is the higher speed, one is the lowest speed, minimum speed 2 centimeter per second. So you can find it is coming like this, and then secondary growth is there. In case of secondary growth is there, in case there is the 3A, there is no secondary growth because your speed is high, to heat transfer coefficient is high. So in that case, the secondary growth has not taken place, because the thermal heat conductance to the thermal boundary layer is little higher here. But what you can find is that red part, that is the bath superheat, has a significant effect. Only 30 to 50, 30, 50 and 80 degree makes a lot of difference. So this is the blue one is the 30 degree, and black one is the 50 degree, and red one is the 80 degree. 80 degree, you can see melting time is much less. So melting time is very low, and prolonged direct heating of the casing in case of high superheat, because the steel growth and dissolving, that doesn't take too much of time, and that's why the casing get exposed for a longer time. And at high superheat also, no secondary growth of the steel cell, even if you have a slag layer over the liquid steel. Speed, effect of speed, this is a very unique phenomenon. Then you can see the general conviction is that if you just pass the wire at a higher speed, then it will penetrate more. But actually, another factor that come into picture, if you just insert the wire at a higher speed, then the velocity of the thermal boundary layer across the wire liquid interface increases, and the heat transfer coefficient increases, and that basically faster the melting of the wire, because heat flux also increases. If you increase the wire speed, that is your thermal boundary layer, that is the liquid velocity increases, thermal boundary layer liquid velocity increases, and as a result heat transfer coefficient increases. That is at much faster rate the heat will transfer through the boundary layer. So as a result the melting will be faster. So it is not, that's why the wire will also melt at a faster rate. At the same time, wire will be moving at a faster rate towards the bottom of the vessel. So these are two counteracting factors. Basically, they optimized what will be the distance traversed by the as a function of speed. So if you just draw distance traversed by the wire versus speed, you can find initially it increases and passes through a maxima, and then it decreases. So there exists an optimum speed at which the wire will traverse the maximum distance, right? So it is not that if you go on increasing the speed, the wire will move faster, because with increasing speed, the conductance through the thermal boundary layer also increases, that try to melt it at a faster rate. So there exists an optimum speed for better performance. And you can see the effect of wear dimensions. Wear has, the code wear has two important dimensions. One is the diameter and is the casing thickness. And you can see here the distance traversed versus the speed, if you can see, and this dotted line representing the 0.4 casing thickness and solid line representing the 0.6 casing thickness, and different colors represent basically different wear diameter, 18, 16 and 13. So we can find that between different colors there is not a much difference in the distance traversed versus speed, but we have definitely a much difference between the dotted line and the solid line, that is when the casing thickness change from 0.4 to 0.6. So that is the makes the difference. So casing thickness has a much more influence on the travel distance rather than its diameter. Okay, so that is very important from here. So the effect of casing thickness more sensitive than the wear diameter. So this is basically we are discussing from a paper that is from the Sharvindu Shandal, Sanjay Chandra, Suresh Kumar and I also one of the co-author, an improved model of cold air injection in steel melt, ISIG International 2004. That time basically Sharvindu Shandal was his PhD scholar, sponsor's PhD scholar from the Tata Steel. I was the supervisor from IIT Kharagpur. Dr. Sanjay Chandra was supervisor from the Tata Steel. And the conclusions, so what we can say, there is the cold air is a hollow cylindrical casing packed with the calcium powder, as I said. The wear is fed into the liquid steel and after it melts is released the powder. For maximum efficacy, actually we have to insert the wear to the bottom of the ladle, and major problem is that in the opaque system we cannot see where the wear is melting. That's why we need a mathematical model. So a mathematical model is reported that can predict the location of the wear melting or how much distance the wear will traverse before it melts. And the model also give a very 4 unique routes of wear melting based on whether the slag is present or not, and high and low superheat. Okay. And the presence of slag layer and the low superheat, it has been found it delays the melting of the wear, and your distance traversed by the wear become maximum at an distance traversed by the wear becomes maximum at an optimum speed. It is not the high or low, certain optimum speed is there, and casing thickness has a more influence on the wear melting than its diameter. Okay. So these are the some what we discuss about this mathematical model of the cold air injection in steel melt, and the most important thing it does, it can give us it can predict for us, that is the location where the wear will melt into the liquid steel or the distance traversed by the wear before it melts in the liquid steel. It is a very important data, because by which we know where the wear is melting actually inside the melt. In the opaque system we cannot see, the modeling can give that idea. Second thing is that it also gives us an understanding. It already identified 4 routes of melting, so we can know what is the mechanism of wear melting. Okay. So now with this model, in the next lecture we will see some industrial implications, how the distance traversed, calculated distance traversed by the wear into the melt will be correlated with the recovery, there is the calcium recovery and as well as calcium recovery. That is the thing, and we will see under the wide industrial operating condition where actually the wear melts. Now we can predict it, and we have predicted from industrial steel plant. That will show into the next lecture. Okay, thank you very much.